producer of ethylene and other petrochemical feedstocks in the world now. The stated capacity is about 3.5 million tons of ethylene, and the actual capacity is supposed to exceed that amount. And we have very little of our own indigenous technologies downstream to utilize those feedstocks. So it really puts a great deal of responsibilities on everybody who's engaged in catalysis to do something about this sorry state of affairs. And thirdly, since the last workshop, the Korean government, through its Science Foundation, established a number of centers of excellence in engineering and science. And we were fortunate, when I say we, the catalytic community was fortunate to have received one of those centers. Unlike the U.S. Engineering Research Center, our center is structured more as a consortium of many university people engaged in catalysis. As a result, we have at present about 30 university people from 9 or 10 universities engaged in research in some major areas. The center was given 2 major mandates. One is, of course, to do a good research on catalysis. The second one was, an equally important one, was to do something for Korea's industries. And so everybody who are here have those 2 mandates in mind in doing their research. Some of the U.S. delegates have just finished attending a meeting in China. In fact, they have arrived last night, and we are very pleased to welcome you all. And we hope this will be one of the best workshops that we have held up to now. And I'd like to, in concluding, express my thanks to Professor Gary Haller, who organized this on the U.S. side. And I would like especially to mention the efforts of Professor Ho-In Lee of Seoul University, who tirelessly organized every aspect of this meeting so that the nominal chairman of the organizing committee could enjoy his stay in Beijing without worrying too much about the actual arrangement of this major function. And now I would like to introduce Professor Gary Haller of Yale University, who is a co-organizer with me for this workshop. He is a professor of chemical engineering at Yale University and currently president of the Catalysis Club or Society Club of USA. Professor Haller.
Thank you, Mr. Kim. My initial interaction with the U.S. and pre-U.S. workshops started back in 1989 when this first workshop was being organized. It's already been mentioned. Michelle Bedard was the co-organizer on the U.S. side. And Michelle called up and asked if I would be the co-U.S. In other words, he was doing the same thing that Professor Kim was doing. He was delegating much of the actual work while he was the actual organizer. So I had put together that delegation with him, and we came here in 1987. Our second meeting we had in 1989 following one of our North American meetings in Dearborn. And I was the organizer of that one, and then we actually missed the 4 years between 89. We had talked about having one every 2 years, but there were a lot of things that got in the way. One was other meetings that were happening. 2 was procrastination on my part, just sitting around and sitting in proposals. And then finally we decided, because of the important changes that Kim has already mentioned here, in the government, industrial, and academic, is that we really should have another workshop, and so we started organizing this about a year ago. For all of you on the U.S. side and also on the Korea side, I must again apologize for the lateness of everything. Everything happened right at the last minute, but the fact that we're all here and most of your needs will have been taken care of suggests that it's going to work out all right in spite of that. I want to mention the objectives that we have in the meeting, and actually I want to mention these in such a way that the U.S. delegates will be careful to send me some kind of comments and reports so that I can use them to report to the National Science Foundation. So it is an obligation as part of the grant money that we have. The objectives are really twofold. One is this informal exchange of information on those frontier areas that are being researched analysis in Korea and in the U.S., and that's what's going to happen in the next 2 days. The second objective is to explore possibilities for mutual cooperation in the future, and at all levels. Exchange of students, we have realistically, must confess that mostly we expect to get some good students from Korea, and we probably won't send many to you. That we want to also have exchanges postdoctoral and sabbatical leave, any of those kinds of interactions. And the one that would be very nice is if there were really sort of the bilateral research projects, and we do have several of those with other countries. I don't know any of them that are actually operative now, but the International Division of the National Science Foundation would be interested in proposals. And so you could be talking to your colleagues here to see if there are some mutual areas where you might actually send some proposals and to try to find out to see if we can get those funded. We're going to have a little session about what happens in the future, probably on one of our bus rides, or maybe down in Pohang, for an hour to try to give us some formal notes that I will use as part of my report to NSF. None of this has to be very detailed, but just if you've had any interactions with Korea in the way of students or postdocs or visits or whatever, I would want you to note those. If any explicit ones that you're talking about that might happen in the future come out of this meeting, those would be even more important to list and send to me so I could convince the National Science Foundation that this is a list of things that are done. I want to end by some thanks and announcements to Professor Kim, who has co-organized the meeting. He's already mentioned Glenn Lee, who is the secretary and our local host here. We want to thank him for all of the things he's done, the little touches, that's some fruit you probably found in the room that night. We appreciate these little details. And we also need to thank those people who are sponsoring this meeting, the Korea Science and Engineering Foundation on the U.S. side, the National Science Foundation, and then also the Catalytic Process Engineering Research Center and the Korea Catalyst Research Association. Finally, some announcements. One of our delegate from the U.S., Lee Thompson, is going to be delayed. He's arriving today. He had a death in the family, and the funeral was on Saturday, so he delayed his trip. I did send a fax to that effect to Pohang, but unfortunately it didn't get here to Seoul, and so people were not aware that he wasn't right. I apologize for that. He will arrive today, and Al and I has agreed to switch with him, so Al will give his talk right after lunch when Lee Thompson is going to present his talk. And then we'll get Lee Thompson to give his talk tomorrow morning. That will allow him to recover for the night rather than coming right in and getting off the plane and giving his talk. Two other announcements. I'd always told you that you might be giving 45-minute talks. I want you to take a third of your few graphs out so you can give 30-minute talks, and I would encourage all of you to try to stick to the program of 30 minutes and allow some time for discussion, because the most important thing that happens in these meetings is the discussion and the informal exchange that occurs now. And finally, for U.S. delegates, would you jot down a couple things that you think are interesting about yourself, like where you've got your degrees and where you're at, and hand it to the chair of your session so that they can properly introduce you. And again, thanks, and I hope we have a nice meeting here on Calvin. And now I'll turn the meeting over to the co-chairs. Yes.
Good morning, everybody. I'm Al Van Ice from Penn State. I will be one of the co-chairs this morning. And the other co-chair is Dr. Hugh Lee, sitting with me at the front table. Before we start this morning, I'd just like to follow up on one of Gary's comments. In order to maximize the discussion after each talk, I would like to suggest to the speakers that they keep their talk between 20 and 25 minutes. This would allow at least 5 and hopefully even more time for discussion afterward, which I think is one of the most worthwhile aspects of a meeting like this. To help bring this about, I just want to inform the speakers I will stand at the end of 20 minutes. And at the end, and this will give you 2 or 3 minutes to conclude. If this does not work, I will chase you with the microphone to convince you that we do need some time for discussion. But with that set of rules, I think we're ready to start, and I think we're right on time. So I will begin by introducing our first speaker this morning, Professor Alex Bell from University of California, Berkeley. Alex received his PhD from MIT in chemical engineering in 1967. While at Berkeley, he was departmental chair from 1981 to 1991. He's currently executive editor of Catalysis Reviews and the U.S. editor of Chemical Engineering Science. Alex has many interests, general interest in heterogeneous catalysis, and I think there are too many to read in detail, but I think this morning he is going to discuss one of these in detail, for which he's quite well known, related to CO hydrogenation. The topic this morning is entitled Isotopic Tracer Studies of the Effect of Olefin Reincorporation on the Dynamics of Fischer-Tropsch Synthesis. Alex?
Good morning. Can everybody hear me? Is the microphone working?
Give it 20 seconds.
Give it 20 seconds to warm up. All right. I think, in fact, most of you, even in the back, can hear me without the microphone, so I will try to work without it. To begin, I'd like to express my appreciation to our Korean hosts and to the organizers of this meeting. This is a wonderful opportunity to come to your country, to become better acquainted with the work that is going on here, and also with your culture. And for me, this is a first visit to Korea, so I'm looking forward with great anticipation to this week that I'll be spending here. The work that I'm going to present to you this morning is the result of an ongoing series of studies that we have had that concern the mechanism and dynamics by which hydrocarbons are formed from CO and hydrogen. This is the reaction that is known as Fischer-Tropsch synthesis. And we can start off by reminding ourselves of some fundamentals of Fischer-Tropsch synthesis that are illustrated here on the first slide. I bring to your attention, first of all, that the reaction produces a spectrum of products, which are mainly normal alkanes and alpha olefins. If one looks at the carbon number distribution of the products, they tend to form what is called a log normal distribution, which can be characterized by this simple expression, in which the characteristic parameter alpha represents the probability of chain growth. And alpha is found empirically to depend on temperature and the partial pressures of the reactants. Now, more recent studies, and in fact studies that are in the literature for some time, some number of decades, going back all the way to Paul Emmett's work in the late 40s, show that the probability of chain growth also depends upon the reincorporation of olefins. That in fact, olefins that are formed as primary products undergo a set of secondary reactions, one of which brings the olefins back into play in the growth of the chains. And therefore, any kind of study of the dynamics of Fischer-Tropsch synthesis has to take this into account. Now, to appreciate what we will be talking about, it's useful to look at a picture of what is known about the mechanism of Fischer-Tropsch synthesis. And this picture emerges from the results of many groups really distributed all over the world. And for ruthenium in particular, which is the metal we will be talking about, the picture that has now emerged and is the consensus view is that gas phase CO adsorbs reversibly to form chemisorbed CO, which then dissociates irreversibly to form a nascent carbon. This nascent carbon then undergoes stepwise hydrogenation to form methine and then methylene units, and these in turn are further hydrogenated to form methyl units. The methyl units then play two roles. One is as precursors to methane, the simplest of the Fischer-Tropsch products, and the other is as chain initiators, in which methyl groups then couple with methylene units to form ethyl units. And this process then can be repeated many times to make a series of longer and longer chain alkyl groups, which then leave the surface either as an alkane, shown here in this case as ethane, or as an olefin, shown in this case as the ethylene. And this is the basis by which we can make methane and the higher molecular weight alkanes and olefins. Now, what has become increasingly important is that these olefins can get reabsorbed and go backwards into the chain growth process. And in particular, ethylene is very effective in doing this kind of reincorporation, as we shall see. And this gives rise to the formation of new chain growth centers, and by depolymerization, we can even form these C1 type fragments that also participate in the polymerization process. Now, the objectives of what we have been doing are shown here. The role of what our recent studies have been aimed at is getting at these rate parameters for initiation, propagation, and termination of the chains. And also this set of rate parameters, these three, which represent the rate coefficients for olefin reabsorption, ethylene depolymerization, and the conversion of methyl back to methylene groups. And a side objective or secondary objective is to estimate the coverages by the C1 and higher alkyl species that are present on the surface. The approach to getting this information is to use isotopic tracer studies. I've outlined the general approach on this transparency. The basic idea is that we take this ruthenium on titania catalyst and we expose it to a mixture of CO, the ordinary CO with the 12 label, and deuterium, allow the catalyst to come to steady state, and then at time zero, we make a sharp transition to a gas mixture with the same composition in terms of partial pressures, but now the CO is C13 labeled. And then we observe, by a technique I'll show you, the distribution of C12 and C13 labeled carbon in the C1 through C8 hydrocarbons as a function of time. And from these analytical results, we can then calculate the fraction of C13 labeled carbon in each of the carbon products. Having gotten the experimental data, we then sit down and we simulate these data from a theoretical model, and then we fit the model results to the experimental results, and from that process extract these rate constants and the other three that are part of the model. And all of this is done with the catalyst and reaction conditions, which I'm showing you here. Now, because the analytical technique that we're using is somewhat different than what you might normally encounter in the literature, I thought I'd take a minute here to just outline that for you. This is an isotopic ratio gas chromatograph mass spectrometer system of our own design. The products from the reactor enter in over here at the left into a sampling valve and are diverted to one of 16 sampling loops, and which sampling loop is chosen is dictated by this microcomputer, which advances this valve every 2 seconds and grabs a sample. And these samples are then stored at 250 degrees Celsius until we have 16 samples, and then each one is in turn returned to this gas chromatograph for analysis. And each analysis takes the better part of an hour. The capillary column over here separates the products into their individual carbon number components, and then further separates olefins from paraffins and a small amount of branch products from the linear products. Each pulse of product comes out and is split into two, one part going to this flame ionization detector to produce an ordinary FID trace, which tells us the product distribution. The other half of the pulse goes through a capillary restrictor. It's blended with a small amount of oxygen in a helium carrier and sent to a capillary tube, very much like the capillary column here, inside which there is a platinum wire threaded in the tube. And all of this is heated to 400 degrees Celsius. The oxygen burns the hydrocarbon pulse, converts it into CO2 and water. There's a natural chemical amplification that occurs here. A product containing N carbon atoms now produces N moles of CO2. So we enhance the number of moles of CO2 relative to the initial moles of hydrocarbon. And the product then goes through a leak valve into a mass spectrometer, where we sit and observe very rapidly the C12 and C13 labeled carbon dioxide. And by this means, we produce two traces, one for mass 45, one for mass 44. So this is the heavy and the light CO2. And by ratioing the areas of the peaks at any carbon number, we can thereby discern the fraction of C13 and C12 in the products. Now, I'll show you the kinds of traces we get out from this system in just a moment. But before that, I wanted to show you two transparencies relating to the effects of the space-time on the steady-state observations that we make, because this already gives us an indirect indication of the role of olefin reincorporation. So here, I show you the turnover frequencies for CO and methane formation as a function of the residence time of the gas in the catalyst bed. It ranges from about 1/10 of a second to slightly over 7/10 of a second. And we can see that there's a slight decrease in the turnover frequency for CO, a marked decrease in the turnover frequency for methane formation, and correspondingly, the probability of chain growth increases by a noticeable amount over here. All of these effects can be traced back to the recapture of olefins, and most particularly of ethylene. In fact, we can simulate these results by taking a low residence time set of results and actually feeding ethylene in, and we will achieve all of the qualitative features that I'm showing you here. Further evidence for the recapture of the olefins can be seen when we look at this plot here, which is a plot of the turnover frequencies for making individual olefins. And here we see that for the C2 products, the ethane production stays relatively constant, which says that very little of the ethylene is being converted to ethane, ethane being produced in a parallel channel to ethylene. But the ethylene production is going downhill steadily. And the reason for that is that ethylene is being recaptured as we go to longer and longer bed residence times, higher and higher concentrations of ethylene, and the ethylene enters into the higher molecular weight products. And that's to be contrasted with what is seen for C4 and other higher hydrocarbons, where there's a decline in the olefin production, but there's a concomitant increase in the production of the corresponding paraffin. And when one adds up these curves, you find that only a small fraction of the C4 olefin can be traced back to making higher molecular weight products. Now let me show you what the transients look like in this system. And it turns out that these transients also depend upon the residence time distribution, residence time in the bed. So here in the upper panel are these what I call F curves, or fractional marking, for C3 through C5. We have a similar curve for C2, and that would pretty much overlay the data here. And this is as a function of the time after the switch from C12 to C13 labeled carbon. And in the bottom panel, the same type of data, but now for C6 through C8. The scatter in the data don't allow us to differentiate very effectively between the transients for the C3 through C5 products, but in the lower panel we can see a clear differentiation for the higher molecular weight products. And in some cases we can even pick up the C9 product, and that would come where I'm tracing with the pointer right now. So clearly there is a delay in the wave as we go to higher and higher molecular weight hydrocarbons. Now we see the same kind of transient if we go to a longer bed residence time. I'll show you that here. Same display of the data. The only thing I'd like to draw your attention to is that with increasing bed residence time, the time it takes to get to a given fractional degree of labeling is extended. And this is counterintuitive. This is not what you would expect if one were only governed by the surface chemistry. And we'll have to come up with an explanation for this delay. And that delay is more pronounced the higher the carbon number that we look at. Now, to interpret the transients that I've just shown you, we've developed a theoretical model, which I've displayed here, or the basis for the theoretical model is displayed here. What we look at are a series of boxes, each one representing a pool of a certain kind of carbon. So here, for example, would be the carbon monoxide. Here would be the monomeric units. View these as CH2 units. Here are the methyl groups, ethyl, propyl, butyl, pentyl, and so forth. And the lines between these boxes represent chemical pathways. So, for example, to go from ethyl to propyl, what we do is add a methylene unit, shown through this arrow here, and then likewise you can see how the chain propagation occurs. Termination is shown by this arrow marked with K sub T, the termination rate coefficient. And counter to what has been done in the past, where the products go directly into the gas phase, we propose that the products pass through a weakly physisorbed state. And the justification for this comes from the recent surface science literature that shows that when you absorb olefins and alkanes onto single crystals, this occurs through a weakly adsorbed precursor state. And we can interpret these results now in terms of this precursor state, and we'll see the importance of the state. The boxes are characterized by time constants, which is the time constant to evacuate that box. And each of these time constants can in turn be related to the rate coefficients for individual processes. And in certain cases, we need either ratios or individual values of certain surface coverages. Now, what we would like to do is, starting with this picture, develop a series of equations to describe the fractional marking, and that's shown here. These are the differential equations that are finally solved, and you'll see that it's a set of first-order linear differential equations in these functions f, which is the fractional marking. The running variable is time, and the only parameters are these taus, the time constants for the various pools. And so what we'll do is solve these equations and then fit the solution to find the time constants. Now, the process of solving these equations can be tedious. It could be done numerically, but we have chosen to do this by the method of Laplace transforms. And I just show you one illustration here. And the reason for finding an analytical solution is that this greatly assists in the final fitting of these transients to the experimental results. And here I show you the type of function that one gets for the C2 through C5 products. It's a very lengthy expression. I draw your attention solely to the fact that there are only 3 parameters in this function. So we can fit, using a nonlinear regression method, this function to the data. The results of that fit, I'll show you next. They're given right here. These are the rate coefficients for termination in the upper panel and propagation in the lower panel as a function of carbon number. And the point to be made here is that these rate coefficients determined from individual transients are essentially constant and not carbon number dependent. And that is a reflection on the quality of the model. In fact, we expect that to be the case. If the model, a simpler model is chosen, in fact, we find that we get a dome-shaped distribution, which is counter to what we should be observing for this kind of model. You also see here that the parameters are not terribly sensitive to the residence time of the gas over the catalyst. Again, something that we would expect this bottle to produce. This latter point is illustrated here in this transparency, where we see how the average value of the rate coefficients for propagation, termination, and initiation depend upon the bed residence time. You see that they're practically independent. The lower panel shows us another output of the model, which are the surface coverages by methyl groups, by methylene groups, and by the sum of all alkyl chains. This is just to give you a feeling of the kind of coverage level that we have. And the total coverage level is somewhere between 2/10 and 3/10 of a monolayer of ruthenium, the balance of the surface being covered by carbon monoxide. We can ask, how realistic are these numbers, since we can't measure them individually here experimentally? The answer is it seems to be fairly good, because we can sum the total carbon inventory here and compare that inventory with a temperature-programmed reduction, something that is relatively easy to do, and we find that we're right on the money, or in very good agreement with the number that we get from temperature-programmed reduction. Let me just summarize these rate coefficients that we finally get out of this analysis. They're shown here, all in units of reciprocal seconds. So the initiation rate coefficient and the reverse step. The reverse step is 10 times as fast as the first step, so this is the methylene back to methyl group. Propagation and depolymerization, termination, and recapture of olefins. And this value is for all olefins higher than ethylene, so C3 and above. And this number is specifically for ethylene. And notice that there are 4 orders of magnitude difference between these numbers, indicating that ethylene is much more rapidly recaptured than any other olefin. And this is consistent with the experimental results. Now, it's more meaningful to look at these results in terms of relative rates. And I'll show you that here. Here we compare the relative rate of termination with the relative rate of recapture of the olefins. And I draw your attention to the results for C3 through C8, and you'll see that for the 2 residence times I've shown you here, it's not until you get to the higher molecular weight products that the olefin recapture becomes significant. And by contrast, I draw your attention to the 2 blue triangles for ethylene, which show that even at the smallest residence times, we're nearly in equilibrium for termination and recapture. So the C2 olefin is very different from all the rest. One last set of results, and then I shall conclude. Here we've summarized the actual rates now for these 3 processes in the forward and reverse directions. This one I've already talked about. The ethyl groups here can depolymerize, and you can see that the rate of depolymerization is about 1/5 of the rate of its formation. And the rate of formation of ethylene groups from methyl groups is of the same order of magnitude as the forward process. And what this means is that if I increase the gas phase concentration of the olefin, ethylene, it can easily work its way back through the system to produce methylene groups and methyl groups. And in fact, this is seen very nicely in a separate set of experiments in which we've labeled the ethylene relative to the CO. Well, let me conclude then with the following points over here. Namely that from a proper analysis of these transient response results, one can obtain actual rates and rate coefficients for individual processes involved in Fischer-Tropsch. The interpretation of these results requires proper accounting for the effects of product holdup in the physisorb layer on the catalyst. Ethylene reincorporation into chain growth is very rapid and leads to the initiation of new chains and the formation of additional CH2 groups, which are the monomer units for making higher molecular weight hydrocarbons. And finally, that for the conditions studied, olefin reincorporation is negligible for the C3 through C8 olefins, but becomes significant for the higher molecular weight olefins. So the final point is that one can get a large amount of information by the proper chemical engineering analysis of the isotopic tracer results that one obtains from such experiments. So with that, I'd like to conclude, and thank you for your attention.
We'll now open the floor up for discussion of this talk. Are there any questions from the audience?
Howard?
Howard?
Howard Salzberg, University of Rochester. Have you any idea why the C9, why the break occurs with reincorporation from C8 to C9?
Yeah, I do. Let me show you something that's relevant to that. Here. This is the time constant for the holdup of olefins as a function of their carbon number. And the thing that you can see is that there's practically a zero holdup here until you get to around C6, and then the curve shoots up very rapidly. And this reflects the fact that as you add each CH2 unit, the heat of adsorption increases by appropriate number, and this enters into an exponential fashion into the heat of adsorption. That's really the reason.
Yes, just a good point. Would you please identify yourself at the beginning of your question? Gary, let me have you, and then there's a question in the back.
Gary Hallett, Yale. My question has to do with the carbon on the surface other than these active species. There are any number of studies for which you are actually co-author on some
Right.
which have carbon pools that are not in your model. And, so there are two parts to the question. One, why isn't that in your model? And two, it doesn't seem like you say there's a good agreement between the total inventory of carbon in these active species and the total you get in the temperature program reduction, which would imply that there isn't any of this carbide or this other non-active carbon being accumulated. So what's different between this system and what we heard about?
Well, we've done the experiment knowing about these other results and running the reaction for a short amount of time so that we don't accumulate large amounts of these other spectator products. Yep.
Can you imagine the location of current flow? I mean, some part may be deposited in the southward, and some part deposited in the southeast. And we also measured some propagation change with time stream. So how can you explain on your mechanism?
If I understand your question, it's what about the possibility that there is a certain number of alkyl groups or whatever you like that is attached to the support. In fact, such products will accumulate on the support if you run this reaction for many, many minutes. And you will also accumulate on the ruthenium a certain number of carbonaceous species which deactivate the catalyst. Now we run, you notice these are not very long runs, 2 or 3 minutes at a shot. We don't run the reaction long enough to see any deactivation or the buildup of these products on the surface. The time constant for the buildup of the products on the surface is significantly longer than the 2 or 3 minutes over which we run these experiments. So while I haven't discussed this, all of this was taken into the consideration in the experimental design. So the experiment is designed to give you the focus on what is going on in the active species pool on the metal.
Research Center for Harvard University and Doctor Institute, Moscow. Dear Professor, please explain me, you analyze only one mechanism which includes species on the surface, CH containing. What is the ground for excluding species which involve CH and O?
Right.
For example, oxymethylated and so on.
Sure.
Thank you.
Yeah. Well, there's a long history of investigation of the mechanism independent of the kinetics dynamics, the specific dynamics that precedes this. And what one can convincingly show is that the rate of CO incorporation into an alkyl to make, say, an acyl group is much slower than the addition of a CH2. The reason for this, if you look for theoretical reasons, is the activation barrier is higher. And over this particular catalyst, ruthenium, you don't make much in the way of aldehyde as a product, and you make no alcohols. In fact, under the conditions where we run, we have neither aldehydes nor alcohols. If you ask, what if you made an acyl group? How easily would you reduce away the oxygen? Again, that represents a much higher energy pathway to making the alkyl than the simpler one of adding CH2 groups. Added to this is the old work done about 10 years or more ago, more than 10 years ago, by Roland Pettit, in which diazomethane, CH2N2, was added to a mixture of CO and hydrogen. And that shows that the CH2 very readily incorporates into the chain growth process. There the CH2 is formed by decomposition of diazomethane. So for all of these reasons, we come to this picture that we have chosen as the one to focus on.
I have a very simple two questions. What in your model you did not include the hydrogen chemistry, also the formation of H2O and CO2.
Right.
Your reaction condition, you cannot observe any those kind of species, CO2, H2O. And the other last question is the recapture of olefin. The rate constant is 200. As far as I remember correctly.
Yep.
That's 2 magnitude or 3 magnitude or the higher in the other elementary step, Kp
Right.
or Ki. So in that, I wonder why is it chemically on the surface?
Okay.
Why is there only
Yep.
C2 unit has a so high reactivity? And if it is so, you better put the ethylene all the time to have more hydrocarbons in the Fischer-Tropsch reaction.
Okay,
Is
let
it
me,
true?
those are both very good questions. Let me answer them individually. The first one is, why don't we account for hydrogen? In fact, if you look at the products, there is water in there, and a little bit of CO2, but not a large amount. So largely the oxygen leaves as water. The reason we don't account for this is by the means that we do the experiment. The catalyst is always at steady state. So the hydrogen coverage never changes with time. Nor does the carbon coverage change with time. It's just the marking in C12, C13. So in this kind of an experiment, we can assume that the hydrogen coverage is constant, and anywhere hydrogen coverage enters into the equations, we capture that into a pseudo first-order rate coefficient. So some of the things I'm showing you are really the product of a second-order rate coefficient times a hydrogen coverage. But since the hydrogen coverage is not time-dependent, I can capture at least the pseudo first-order rate coefficient. So that's the first question. The second question is, why is the ethylene reincorporation rate so much faster than the other olefins? I don't have a completely convincing answer for that, other than to say that very likely it has to do with the chain length and the entropic issues here. As you make a longer and longer chain, to get the olefin to absorb on two metal centers becomes more and more difficult on a surface that is completely saturated with CO and alkyl species. This is a highly covered surface. The total coverage by all species is close to 1. And I think that's the reason. Experimentally, certainly, it's supported by the fact that if you add olefins of different chain length, the C2 olefin goes in much more rapidly, orders of magnitude more rapidly than higher molecular weight hydrocarbons. And that's not an observation unique to us. It's been observed in several laboratories.
Well, in the interest of seeing a schedule, I unfortunately will have to disallow the other questions that exist. But Alex, we'd like to thank you again.
Good morning, very much. My name is Lee. I'm here from Korea Research Institute of Chemical Technology. It is located about 150 kilometers south of Seoul. I will present the second topic this morning. Dr. Chong-Sik Chung will present the title of phase cooperation of multi-phase molybdenum